Hello, everyone. This is Paul Fischione. Dr. Pavel Nowakowski and I would like to welcome you to the introduction of our Model 1064 chip mill. This is a large-scale ion beam delayering of microelectronic devices yielding nanometer flatness. Before we begin, please use the question feature to submit your questions to the presenters throughout the presentation. All of the questions will be answered at the end. And naturally, if you'd like to have a follow-up conversation, please schedule it by contacting us at sales@fischione.com. And that can pertain to both the chip mill and any of our other products. So with that, I am pleased to introduce the Model 1064 chip mill. This is the most exciting specimen preparation device since the introduction of the FIB in the late 1990s for TEM specimen preparation. The chip mill is truly disruptive technology. And aside from the performance, it has the most advanced technology ever incorporated into an ion milling system. Before we begin to discuss the chip mill, I'd like to provide a little bit of a background of the history of ion milling and Fischione instruments. Here at Fischione, we have 3 decades of TEM ion milling excellence. Our first ion mill for TEM applications was introduced at the Boston M&M meeting in 1992. Since that time, we've continued innovation and excellence in ion milling for TEM, with the latest offering being our Model 1051 TEM mill. As many of you well know, our Model 1040 Nanomill and Model 1080 Pico Mill both yield TEM specimens that are unsurpassed in quality, free from amorphous damage and implanted layers. With our basis in history in TEM, we expanded our offerings to include SEM sample preparation. And the largest drive there was due to the market. We saw the need as a result of improved imaging at low voltage SEM operation. And what that does is that places greater demands on the quality of the sample surface. So about 15 years ago, we leveraged our TEM specimen preparation knowledge, branching into SEM applications. The product offerings that we've responded with have been a series through the years over the last 15 years, with the Model 1061 SEM mill and Model 1062 Trion mill being the latest introductions to the product line. The key to the technology is through increasing our core competencies in argon ion beam technology. And we have pioneered techniques to use various size and energy argon ion beams to create these very pristine sample surfaces. Currently, we're able to provide ultimate sample quality without damage, implantation, and either chemical or physical alteration. And this is consistent from the original days of Ernst Ruska, where the specimen needs to be representative of the material in the bulk state. That was a brief synopsis of the past. Now I'd like to start talking about the future and the chip mill in more specific detail. And the chip mill is very much a result of responding to the market needs. For the past several years, our research has determined the need for the precise delayering of semiconductor devices. And the desire was to establish nanometer flatness over a millimeter scale or several millimeter scale for both memory and logic devices. Up to this point, there have been a few alternative technologies, beginning with mechanical preparation. When a sample is mechanically prepared, it oftentimes lacks the precision in terms of endpointing. It's also very easy to introduce damage in terms of cracks or surface strain, and it's time intensive. And as you can imagine, as device sizes in the semiconductor are decreasing 7 nanometer, 5 nanometer, 3 nanometer and beyond, any type of even sub-micron scratching is detrimental to the imaging and analysis. Focused ion beam technology, whether it is gallium in a traditional fib or xenon in a plasma fib, is currently used for delayering purposes. They're both excellent tools in yielding precise site selectivity. However, the area created is relatively small, being on the scale of either tens of microns or a few hundreds of microns. And finally, the broad ion beam milling. And as I previously stated, this is very much in the Fischione wheelhouse. We've been able to create relatively large milling areas, up to about 2 millimeters. However, because this is a traditional low angle milling system with a sample rotating, we're not able to produce truly planar surfaces. So combining all of this background information and feeding it into the development of the chip mill, it definitely takes the large scale delayering to an entirely new level. This slide is an example of the relative milled areas. On the left is a 200 by 200 micron square window produced by a PFib. Broad ion beam milling, as I previously stated, applies a surface flatness within a 2 millimeter area with a flatness in the 180 nanometer range. The chip mill, and I'm very pleased to say this and show it, is able to produce a planar sample surface up to 8 to 10 millimeters with a flatness of 50 nanometers over the entire sample surface. The key to the technology is the ion source itself. We have developed a columnar argon ion beam with a diameter of approximately 0.5 millimeter. We're able to project that over a long working distance. And because of the ion optics, we are able to raster that beam in a given pattern within a given area. The ion beam itself is controlled by a feedback loop that we'll be talking about in more detail. As you can see from the image below, the ion beam projects over the sample surface while it's rotating, and the beam rasters during the process. As I said previously, we've incorporated many, many different technologies into the chip mill, and it begins with the ion source, the ion optics. We also added an electron beam column. It's very similar to what we're using in our Model 1080 Pico mill. Now that we have electrons, we're able to utilize various detector technologies. With the electrons, we're able to image the backscattered electrons, secondaries, and also create X-rays that are detected by the EDS system. In addition to the traditional types of detector technology, we've also incorporated a secondary ion mass spectrometer. Now, the key to all of this is taking these detector technologies and utilizing artificial intelligence for ion beam control. The processing is automated. The data collected from the detectors are processed by the AI ion beam control algorithm. As I previously mentioned, in this feedback control loop, the algorithm adjusts the milling parameters, including the uniformity factor. And I'm just going to pause there because the uniformity factor is the key to the technology. That's the secret sauce that makes this work. So we'll be talking about that in more detail. That's what yields the highly planar sample surfaces. And the good news is, from the user perspective, all of these actions happen in the background and are totally transparent. This shows the sequence of operation. This is an argon ion milling system, so it begins with the argon ion milling. During the process, we have periodic data collection. We're grabbing signals at the appropriate time in terms of the backscattered, the EDS, and the SIMS. The artificial intelligence algorithm is processing the data to determine the current layer and to assess the planarity, and that's the key component. In real time, we're able to adjust the milling parameters in terms of the uniformity factor, here it is again, the raster size, the milling angle, and the beam energy. These are some examples of the periodic data collection. The images on the left are the backscatter electron detector images, and you'll notice they're taken at two different voltages, at 5 kV and at 10 kV. At 5 kV, we're predominantly looking for the sample surface. By increasing the voltage, we begin to look at the sublayer. And that is a key aspect in the algorithm for determining the topography of the specimen. The EDS system determines the chemical composition of the layers in a very traditional manner, and the SIMS identifies the top device layer, whether it is an oxide, a nitride, or a metal layer. Again, going back to the uniformity factor. These are three examples of the milling profile. And you'll notice on the left, there's a number 1 and a number 10. For illustrative purposes, we're using that as a range of change in the uniformity factor. Looking at the sample, which sits on a standard SEM stub from the side view, with a uniformity factor of 1, material is predominantly removed from the center. creating a small dimple, which is representative of pretty much traditional argon ion beam milling. Increasing the uniformity factor to 10 changes the raster pattern, and in this case, with a factor of 10, material is removed primarily from the edge. So you have a high spot at the very edge, the periphery, you have a high spot in the center, in the preferential milling close to the edge. The artificial intelligence automatically adjusts that uniformity factor in real time to achieve the uniform delayering from the center to the edge. And it does that by basically altering the raster pattern in very simplistic terms, controlling the dwell time per pixel. Now, the purpose of electrons, and I want to be explicitly clear on this. The ChipMill contains scanning electron optics, but it is not for discrete imaging and analytical purposes. The electron beam has been optimized to balance the precise ion beam control with the speed of overall total sample processing. The signals created by the interaction of the electrons with the sample surface are captured by the detector. The detector outputs are fed into the AI algorithm that specifically controls the ion beam raster pattern. And based on the surface topography, the algorithm automatically adjusts the uniformity factor in real time to achieve the sample flatness. The algorithm can sense if you're milling higher in or milling more in the center, adjusting the beam toward the periphery, or if the edges are milling more, it backs off on the dwell time in those given areas to generate the sample surface flatness. And just to summarize with the artificial intelligence, it truly is an autonomous system. The ChipMill closed loops the process in 3 repeating phases. It senses by having the detectors collect the information from the sample. It thinks by collecting this information and analyzing it, and then it acts based upon the analysis. The AI modifies the milling parameters as needed, and the ion milling continues. This closed loop occurs without the user intervention, which makes this truly exciting technology. So with that, I will conclude the background of the system and turn it over to Pavel for the application section.
Thank you, Paul. Hello, everybody. So now I will move to the application part of presentation, and I will show you some very exciting ChipMill applications for different device delayering. So what is delayering? Delayering is the process that allows you the control removal device layer per layer, as you can see here on that representation. For LED, it could be yield enhancement, failure analysis, quality control, or reverse engineering. So there is a lot of application when the ChipMill can be used. And then overall goal of the layering process is that after we expose a large area of only one layer, achieving the planarity with a maximum tolerance of 15 nanometers over millimeter scale area. As you can see here on that representation, You would like to get large area with nanoscale flatness and very shallow profile. So now I will move to the first example of the layering process made by ChipMill and show you how the system is dealing with thick layers. So here we have a device, is a memory type device. On the top we have the thick layers, we have silicon nitride, we have silicon oxide, we have thick aluminum layer. There is also the copper layers here and memory device over here. So we place the sample to the ChipMill. Then user can set up the ion beam energy and raster size and define the region of interest. The goal here is to remove the thick top layers and stop on the aluminum layer just on the top of it, as you can see here. So user has to indicate to ChipMill that remove 2 layers and stop on the top of third aluminum layer. Those are only parameters defined by user. The uniformity factor and milling angle are the parameters set up by artificial intelligence based on device surface characteristics. From now on, the ChipMill is completely autonomous and drive the process without any user intervention. So after the process, the ChipMill removes about 1.8 micron of material and supposed to stop at the top of the aluminum layer here. And effectively, we take out the sample, we examine it, and we observe that ChipMill obtained the very large 8 mm diameter area when only one layer is exposed. In this case is aluminum, as you can see here from this EDS data. So now let's check how uniform is that milling area. So because the sample rotates during the process, we did the fib cross-section at the center, outer, and at the edge of milling area. Then the thickness of aluminum line was measured. And as you can see here, those measurements shown that we obtained the surface flatness within 50 nanometers over an 8 millimeters area. So as you can see, ChipMill can remove a lot of material and keep uniform surface profile during the process. So now I will move to second example. You will see how ChipMill is dealing with precise delayering of thin layers. And I will give you more details on how the ChipMill drive the delayering process. So before ion milling starting, it's very good to collect information about the chip, like how many layers there is, their thickness, the composition, the nature. Is it a metal layer? Is it a via? Maybe the contact layers is the layer of interest. There is gate. Is it the logic device or memory device? Then the sample is aligned to the center of the stage rotation, which is also the milling center. Then ChipMill takes control over the process. It's taking the backscatter images from different locations using different voltages. As you can see here, we have 5 kilovolt backscatter image when only top layer can be seen. As you can see here, M2 is on the top, as you can see on this cross section also. However, if you take the images at 10 kilovolts, you will see them M2 on the top and metal layer 1 underneath. ChipMill is also collecting the EDS data. And as you can see here, the top copper layer is very uniform. So using all that information, the backscatter images and EDS collected before milling, ChipMill determines uniformity profile across region of interest, which can be defined by user. As you can see here, the chip surface is very uniform. Then ChipMill, using artificial intelligence, determine the starting conditions of milling. Only ion beam energy and raster size can be defined by the user. And this is possible only at the beginning of the process. After that, ChipMill is completely autonomous. All actions happen in background and are transparent for the user. So how this works, how ChipMill determine the flatness of the surface. So periodically, ChipMill stops milling and collect needed information in order to assess the surface flatness. The presented here high-resolution images are not ChipMill output. These images were taken only for presentation purpose and to validate the accuracy of the artificial intelligent algorithm. So here you have example of first iteration. The backscatter images were taken from different locations and different voltages. Then the data are compared from what was before and after the first iteration. As you can see here, the material is being removed. Layer M2 is getting thinner. Now at 5 kiloelectronvolts, you can see the metal layer 1 underneath of the metal layer 2, what was not observed before milling start. Using all that collected data, ChipMill determined uniformity profile. As you can see here, it was found, but there is no enough milling in the center the sample. Using that information, artificial intelligence adjusts the milling parameter by concentrating milling in the center by changing raster size and uniformity factor. Those actions are completely transparent for the user. ChipMill is completely autonomous. The artificial intelligence modifies the milling parameters as needed and ion milling continues. And after some time, ChipMill stopped milling in order to assess the effectiveness of made changes. So after second iteration, you can see that metal layer 2 is almost removed. However, the large copper lines, as you can see here, still remain on the surface. You can see now, even at 3 kilovolt, the metal layer 1. ChipMill determines uniformity profile once again, concludes that uniformity in the center was improved. You can see that nicely here. However, we got some non-uniformity in the outer area. In order to correct that, ChipMill adjusts the milling parameters, increasing ion beam energy, the raster size, and uniformity factor. At that time, ChipMill decreased milling angle. So after third iteration, ChipMill determined that only via layer is now exposed. As you can see here, the small bright contrast dots here, you can see them over here, are the vias. So layer M2 is completely removed, exposing very clean surface. ChipMill assesses the uniformity profile and determine that the flatness across region of interest was reached. And effectively, we examined the sample by making FIB control cross-section. In the center, 2 millimeters from the center, and 4 millimeters from the center at the edge of milling area. Then we observe the cross-section using the stem. As you can see here, this confirmed that we reach the surface flatness within 50 nanometers over 8 millimeters area. And with this statement, I will finish the application presentation and I give back to Paul for conclusion. Thank you very much.
Well, Pavel, thank you for the presentation, those great results. I think everybody can now see that the ChipMill can precisely control an argon ion beam to selectively delayer the semiconductor device. And it's independent of the elemental composition and the device geometry. And as we said at the very beginning, this is truly disruptive technology, taking the specimen preparation and delayering to an entirely different level. So with that, I would like to conclude by thanking just a few groups of people. As you may have seen on some of the slides, I'd like to thank the Sandia National Laboratory in Albuquerque. They've been great providing the sample materials to us and then taking the as chip milled samples back and doing high-level quantitative imaging and analysis. This has been really key for the depth profiling, so really do appreciate all the work that Sandia has done. And I'd also like to extend special thanks to all the Fischione staff, not only for the folks that put together this presentation, but for all of the work that's transpired over almost the last decade in developing the ChipMill technology. We really feel that we're positioning ourselves extremely well for the future in this particular market. So with that, I can see that there's a series of questions coming in, and be happy to start going through them. The first question is, does the ChipMill work for both aluminum and copper chips? Pavel, do you want to take care of that one, please?
Yes, of course. This is a very good question. Yes, ChipMill can delay any layer. It is metal layer, or this is silicon oxide or silicon nitride or tungsten. There is no problem.
Good. The next question is, what is the maximum raster size setting and the corresponding uniform area? The maximum raster size is 10 millimeter. And the uniform area represents the majority of that 10 millimeter. You do get a little bit of an edge effect because of the tail of the beam. But let's just say the majority, 80 or 90% of that raster box or raster diameter, raster size, is within, as Pavel stated, 50 nanometers of flatness, which is pretty incredible. More questions coming in. This is great. Really good questions. Pavel, if you want to take this one, do you need knowledge about the device layers before the delayering process?
Very good question. So it's very good to know, but you don't have to know. ChipMill has a lot of detectors and can detect the layers, the composition, and which layer is on the top, which layer is underneath. The seams played a very important role because can catch, can sense the information right from the very, very top. So which we hit the new layer, the SIMs immediately detect that, and we know we are on the new layer. So it's good to know, but you don't have to.
Okay, good. Next question. What is the throughput time for the use case where you're removing the thick layer? If you're talking total throughput time, there's a load lock on the front. Pump down and venting times are certainly less than a minute, so the majority of time is involved in the delayering process and image and analytical data capture. Milling rates are obviously dependent on the material. They're obviously dependent on the raster size. The smaller the raster size, the higher the energy, the more rapid the milling rate. But what we can say is throughout the development, we've been pretty focused on creating as large an area as possible. So we've been using raster sizes on the order of 8 to 10 millimeters. And the milling rate is on the order of about 1 to 3 nanometers per minute. So it's careful enough to remove without damage, but it is rapid enough to go through relatively large layers in short periods of time. The real forte is when you get into either the metal layers or the memory stacks, where you're removing tens or a few hundreds of nanometers of material. Next question, how important is surface roughness? Could the ChipMill planarize a sample with 200 nanometer roughness and then find accurate subsurface interfaces? Wow, okay. Yeah, naturally, and this goes back through all of our expertise in ion milling over the past 3 decades. The better the surface quality going in, the better the results coming out are. You know, I would not purposefully put in a surface that's extremely rough. I would take it through any type of standard technique. But the key is the image capture pixel by pixel and analytical data capture pixel by pixel, and then driving the beam to where the beam needs to do the most work, and then speeding over the areas where the beam does the least work. So yes, it can planarize a rough surface. And the second part of that question, looking for accurate subsurface interfaces. We understand the proprietary nature of the semiconductor industry. And there's certain information that you have that you probably will not be divulging to us. So the ChipMill is intended with the artificial intelligence and the machine learning to essentially build a library of information. And if you're doing a repetitive chip type, then you'll have that and ultimately be able to endpoint at the desired layer. Next question, how good is the response of the AI to new unknown materials? That's an extension of the last question. The AI is picking that up pretty much pixel by pixel and analyzing. Pavel, if you want to take the next question, how is the die mounted in the tool?
Sorry, how is what?
How is the die, how is the chip mounted in the tool?
How is mount? It can be mounted by silver paste or copper tape or carbon tape.
Okay, next question. Is there the ability to save a configuration for future use on the same type of part? I believe that I answered that in the previous response. The answer is yes, that a library can be built and ultimately recipes can be restored and processed for the same particular die type. Next question. Pablo, if you want to take this one, do you need an initial planar flat surface, or can it also correct the surface with significant local topography, say a couple of microns?
It's better to have the starting surface flat. It's as Paul said, the better sample is before, the better are the results. But ChipMill is able to planarize some degree of non-uniformity before process.
Okay, great. Next question. What is the ion beam angle range and how does it change? That is a really great question. Let's talk a little bit about the physics of it. If you recall the image where the ion beam was projecting over the sample surface, we're obviously rastering in one direction. We also have the Y deflection, which tips the beam down toward the sample surface. In addition to the Y deflection, as we've done with many of our other SEM tools through the years, we have automatic height detection for the sample. So we're able to alter the Z height, the planar position of the sample, and also the deflection of the ion beam, translating to milling angles anywhere from 0, which is not practical, up to about 10 degrees. Next question. We keep getting the same question. It's probably just the sequence that's coming in. And I'll touch on this. Do you need to flatten the sample surface before milling with the chip mill? Naturally, the better quality you put in, the better results you're going to have out. Next question. Chip top layers measure about 2.8 microns. What's the maximum thickness this tool can remove? The thickness removal is pretty much just a function of time. If you do the calculation of 1 to 3 nanometers per minute, you can establish how long it will take to remove any given layer. Next question, as the AI recalculates during the process, does it capture images that can be viewed after the fact? As I said earlier on, this is not an imaging or analytical tool. These things are being processed. The signals are being processed in real time to create the planar sample surfaces. Next question. Could this in theory be used to create a plan view TEM sample if the starting sample is tens of microns thick? That's a great question. I need to think about what the result is going to be, because in theory, it's probably, the answer would be yes. We would need to experiment with that, because keep in mind that the beam diameter is 0.5 millimeter. How that would work on a 3 millimeter diameter disc or a fib lamella, that would need some level of experimentation. Next question. Is targeting of individual layer possible For example, my device has 7 layers and I would like to stop the process on layer 3, remove 4 top layers. Is that automatic? Pavel, do you want to take that one, please?
Yes, that is a very good question. So yes, this is possible, but of course, in that case, you will have to know the structure of your device and input that data to the chip. And let's say, basically say to the chip, okay, I have these layers. It looks like that. I want to stop at this given layer, and then it's automatic. ChipMill will take control, and we stop at the desired layer.
Okay, good. Next question is another one that came in for TEM specimen preparation, which we've addressed. What is the biggest sample that the mill can handle? It is a sample that fits on a 1-inch diameter standard SEM stub. Is there some image outputs from the chip mill to judge if stopping or continuing the delayering process? The answer to that is yes. Are there temperature controls implemented for the stage? Currently, no. And the reason behind that, and we've had a lot of expertise in terms of the TEM specimen preparation, where it's highly beneficial to utilize liquid nitrogen specimen cooling. But there you're talking a lamella or a thickness of just a few atomic planes and ion beams that are significantly higher in energy. For the chip mill, because of the beam current and current density as it rasters over the surface, combined with the very large heat-seeking or heat-sinking capabilities of an SEM sample, we have not seen that temperature controls of the stage are necessary. All of the work that we've done has been at room temperature. Next question, can chips be batch processed or is this a serial process? With a load lock, only one sample can be processed at a time. Next question, can the SIMS work with the EDS to stop 20 nanometers short of a new layer? Pavel, would you like to answer that one, please?
Yes, of course this would be possible. All detectors interact together. All the information are collected and processed by artificial intelligence. So there is not separate like there is no view separate to one detector to another. Everything is collected and then processed as one information. So yes, all detectors talk together, and you can stop a desired layer.
Okay, next question is also for you, Pavel. How is the roughness measured 3D or gray level intensity?
I I don't get the question, sorry.
Okay, how is the roughness measured? And I guess if you want to talk a little bit about once it's chip milled, putting it into the fib and doing the cross section down to the layer.
How we control, yes.
And then also the AFM work that was done at Sandia.
Yes, so we control the flatness using the fib cross section. So we took out the chip and just put in the fib and cut several cross section through the milling area. Then look at the stem and measure what was above. We measure the roughness of of the surface across whole area, and also we did the IFM measurements of the surface, and those measurements showed us that we are able, and ChipMill is able to achieve the flatness over large area within 50 nanometers.
Okay, excellent. Next question, please define the relationships of the KV and beam angle toward the size of the region of interest uniformity. Really a great question, because the beam is electrostatically deflected with the Y deflectors. There is the correlation between the accelerating voltage and the voltage bias on the deflectors. The key to it is making sure that the impingement point of the beam is on the axis of rotation of the sample, and that's done during the process setup. Once that's achieved, the uniformity in the region of interest is identical from sample to sample. You're putting the ions exactly where they need to do the work, and you're rastering them in a fashion that the detectors are capturing the data, processing it, and then changing the raster pattern in real time. So all of those things are taken into consideration, and they all happen, as Pavel said, autonomously behind the scenes. Next question, pricing. We will not be discussing pricing today. We will be back in touch with you with the corresponding price quotations. Next question, can the ChipMill correct the thickness uniformity of a film that is smooth, but has, say, center to edge thickness variation or a wedge thickness profile from one edge to the other? Pavel, can you take that one, please?
Yes, yes, that can be corrected. That is exactly what ChipMill does. Can correct the changing the uniformity factor, the meaning over the large area, meaning more on the outer, in the center, or whatever meaning is needed. So you can correct the flatness of any surface which in the flatness is smooth but different with the variation. I would like to say, yes.
Right. Yeah, I'd like to hedge a little bit on that answer. I'd be concerned about a wedge profile because the sample is rotating. I'd have to see how that would react. But certainly, if it's relatively planar and or if it's uneven within a given diameter, as Pavel said, it's designed to smooth in that area. Would need to experiment on the wedge thickness. Next question, does the ion gun require frequent, weekly, fortnightly maintenance as 1061 gun requires? And what is the maintenance schedule? So there's two questions there. The ion source is based on electron impact technology using a filament-based system to create the electrons that go into the ionization chamber. Filament life is now running on the order of about 200 hours. Next question, Pavel, if you could take this one. Where do you see the ChipMill being used in the semiconductor life cycle, R&D, manufacturing, or failure analysis?
We'll see them all that field, I think.
Okay. Next question, what is the footprint of the tool? I apologize, I actually don't have that in front of me. It's about 48 to 50 inches wide. It's about 72 inches tall, and the depth is about 30 inches. The information, the literature will be on our website, and that is included in there. Next question, how do you navigate to a POI, position of interest? Pablo, do you want to take that one?
So you will align the sample, the region of interest. The sample will be aligned to the center of the rotation, or you align the region of interest to the center of the stage rotation. This is the both possibility. If you align the sample to the center of the rotation, and then your region of interest is a little bit off of that, like we show on our example. So the meaning is always regarding to the center of the rotation, but you can define the region of interest which is off of the center, and then the ChipMill will focus on that region of interest. But you always mill around the center of the rotation, of the stage rotation.
Right, and there's a follow-up question to that. Is it similar to your other ion mills in which I can draw a raster box on a particular area of the sample? So along those lines, you set up the size of the raster, and the milling occurs within that raster pattern. So I believe that that is the last question that has come in. Naturally, if there's anything else that comes up as you go through the thought process, feel free to email us directly or through sales@fischione.com. I just very much want to, again, extend appreciation to all the Fischione staff for making this happen, our collaborators at Sandia, and especially for all of you that took the time to attend today. I hope that you walk away with the feeling that this is truly some game-changing technology, and look forward to working with you to build a justification for the system going forward. So thank you for your attendance, and I wish you a good day. Bye-bye.